So if you want to make a note for this title of the article, eventually it shows that if you use a simple NMOS as a switch, as we all know, NMOS is not good at passing ones, right? So in that case, we want to switch to a transmission gate, so you have PMOS and NMOS at the same time. If you have PMOS and NMOS at the same time, you think, hey, probably it's going to be fine. Okay, it's going to be fine. However, it's still not fine. So the reason for that is because your clock, your gate voltage, is fixed at VDD or ground. Okay, let's say if it's VDD, it's a DC voltage. And what's happening is V in, VDD, and let's say this is ground. Okay, when it's passing V into the other side of the circuit. So your VDD is basically a battery, right? And it's grounded to the physical ground. So in that case, when V in changes, your VGS changes. Because VG is not changing. VG is just a VDD. It's a battery, right? It's a battery. However, we are looking at VGS. Remember the square law equation? IDS equals KPN over 2 W over L, and VGS minus VTH minus VTHN square, right? It's a square law equation to determine the IDS, so the current running through the channel of the transistors, right? So if the current is changing, you can tell that if you run the simulation for the channel resistance, and you are seeing this. Okay, so this is V in, this is the signal, okay, keep in mind, this is signal, and that's the channel resistance. It's changing like this. It's not a constant. Since we learned something in the beginning of the semester, okay, there's a cap, right? So there's a cap. This is how I model it. This is R on of the transistor. You can see the changes are very significant. It's from like 50 ohms to 350 or 400 ohms. Okay? I can see if you have a R, which is the channel resistance, and a cap, from V in to V out, there will be what? There will be a 0.7 RC time delay. So what is that problem? So you have a sine wave, okay, sine wave of signal, and you are trying to pass the signal, not losing anything to the output, just the entire signal to the output. But because of the time delay, whenever the voltage of the V in changes, and the time delay changes, so we're not exactly copying the V in. So what's actually happening is your V out becomes, hey, the voltage is over here, probably the time delay is not as much as the higher voltages. With higher voltages, then the time delay changes to this, and the sine wave eventually becomes a signal like this. Even though it's not exactly, but you know, because of the time delay is changing, right? The channel resistance changing, eventually you are not recovering your V in over here. So when we are doing the ADC conversion, so eventually your signal will not be as accurate as the ones that is able to keep a constant channel resistance. And this is called distortion of the signal. And how to analyze the distortion quantitatively? Okay, after Dr. Razavi published this article in the magazine in 2015, I guess. Yeah, 2015, when I was in graduate school. And there are probably a lot of people asking him, email the editor in chief of the magazine, like how to analyze the distortion. And a few years later, he published another article on that to analyze the distortion in the frequency domain. So if you are interested in that, you can look into the details of the articles. Okay, in the future if you want. So that's the title of the article. So how to solve the problem? How to solve the problem? So there's a circuit design called Bootstrapped circuit. So because now the problem is that VGS is not constant. Why the VGS is not constant? Because whenever you turn on the switch, it's a VDD, your VIN is always changing. If VIN is changing, then your VGS is changing. Makes sense, right? And that is why your it's causing distortion. Okay, so can we design a circuit to keep your VGS a constant? So that is the question. Okay, so we need electrical engineers to design the circuit to make it constant for the sum and hold circuit. So the idea in the model, okay, so the ideal model for that circuit looks like this. You can still put your V over here, and that's your holding capacitor. So V is a signal, right? It's a signal. And because the reason that we call this VE is because it's compared to ground, it is VE. Okay, it's like a battery, but it's a varying signal that is grounded. Compared to the previous VDD, we connect to VG, and this VG is a little bit different. Could you tell me the difference here? What's the difference of the VDD in terms of connections? This VDD is not grounded. Cathode is not grounded. Cathode is shorted to the source of the NMOS. So eventually, you are forming a constant drop from G to S. So in that case, your VGS is not changing. Can you trust it? Is it changing? You can trust it. It's not changing because this is a voltage source, the ideal source. It tells you it's VDD. It's going to be VDD forever. Okay? It's going to be VDD forever. So if you can do this and put your V in over here, so another question for you guys is VG changing or not? Why? So whenever V is pushing, right, it's adding this one, adding V into the cathode of the VDD. Eventually, you are forming a series. If you consider this as a battery, so eventually VG becomes a varying signal sitting on the top of VDD. Okay, so VDD becomes a DC offset. Okay, so we're adding this AC signal to a DC signal. So VG is changing. However, VGS is not changing. And VGS is the one we are looking at. Okay, so the square law equation, and there's another equation we didn't discuss, which is a channel resistance. Was derived from the square law equation, right? So it's all depending on VGS. VGS not changing, these parameters are not changing. So how do we implement this circuit? We can design switches, and we know how to design switches just using transistors. So if you can design a circuit like this, Sorry, it's a switch. What about something like this? So if you close these switches, let's call it M1, M2, M3, M4, M6. So M stands for MOSFETs. So these switches are eventually transistors. You can model them as transistors. So when M1, M2 are closed, C1 charges up to what? Let's keep it consistent. Charge up to VDD. Is the capacitor shorted to ground? Nope. So it's like a floating capacitor. You close the switches and you dump charges to the cap. So it's actually charging up the cap to VDD. Okay, you got VDD and ground over here. You close these two switches, boom. So keep these open, okay? So you close the switches and the capacitor is gonna hold VDD on it. And then you open it, so this cap becomes a capacitor which holds a floating charges. It's just stored in the capacitor without being discharged to anywhere. Like a close, charge it up, open the switch. So the capacitor is able to hold a VDD across it. Okay? It's trapped in there. It's not going to anywhere. Then the next, you close M3 and M4, then what's gonna happen? Yeah, so VGS equals VD. Okay? Now you can do what? So whenever I have a VDD across it, you are ready to do what? So signal comes in, it's adding to this VDD, and it's not changing the VGS over here. So it's actually sampling, right? Sampling. So signal passes through it. It's sampling. So during this period, do we want to keep M6 open or closed during this period? M6 should be open or closed? Open. Why? If you close M6, what's going to happen? The previously charged capacitor will be discharged to ground. Its charges will go back to ground. So you're losing that floating charge. If you're losing that floating VDD over here, then if you ground it, this NMOS is off. So nothing's gonna happen. You're discharging VDD, and this NMOS is off, and eventually Vin comes into this node. It's not going to pass. Will not be passed to the other side of the NMOS. So what is happening during that phase? Just one word. Hold. Here. Then what about this one? What about this one? What about this phase? What's the name of this phase? Okay, so for this one, M6 is closed, right? For this one. And for this one, if these two are closed, M6 is open, all right? Signal comes in, as keeping a constant VGS is on, always on, and constant VGS. So V is able to arrive here and then chart of the cap. So this becomes the output of the sample and hold. And this phase is, the name of this phase is sample and track. Is it tracking? Is it tracking? Like I got a V in like this. Is this just sampling this point or is it tracking? It's tracking because it's on. So it's tracking. So when it stops tracking? Yeah, when M6 is closed. What's gonna happen? This still go on as a sine wave. What's happening here? Hold. Make sense? So eventually, tracking means whatever this here is doing is going to do the same. It's tracking, following or tracking. Okay, so a lot of times it's called sample and track and hold circuit, not just sample and hold. Sample and track and hold. So let's see. You guys tell me when it samples, when it tracks, when it holds. Okay, so I got this sine wave doing this, all right, and output also doing this when it's tracking. Okay, so this is tracking during this period. It's tracking. So when M6 is closed, this is still going on like a sine wave, and at this moment, it holds it. So this period is hold, and which point is sampled? Which point got sampled? This point or this point? Of course, this point, okay, because the value getting held is the same value as at the last point of this tracked curve. Okay, now let's take a look at the example here. So the circuit we're going to build will do a sample and track and hold. And the black line is the sine wave. I just zoomed in for my few times. So here, the black line is the sine wave, and this is the signal of the sample and hold circuit. So turn on and then starts tracking. Here you see the red line is tracking the black line. There will be a time delay, but we'll start tracking. Okay, and then whenever it stops, or the M6 closed, it's going to hold the value over here. So imagine once this is being held at this moment, at this point, or this value, you should start your ADC conversion using the SAR logic as soon as possible. Okay, you can delay a little bit, but however, it's just super unnecessary. It's a waste of time, right? Okay, so the goal for the next few 10-20 minutes is to build that, to understand the sample and hold circuit and build it. Okay. So last time we talked about a circuit looks like this. Okay, VDD. So because the first cycle, the NOSes are still losing one VTHN, but after the first cycle, because the VG, both of the VGs are getting a value which is larger than VDD, so eventually it's able to pull the entire VDD to these 2 points. So eventually this point is going to oscillate from VDD to VDD. I'll do this really quick, okay? So whenever this guy is pushing, this is pulling. If this is pushing, this is pulling, and the voltage over here becomes VDD. And because this is pushing, so it's a 1, okay? If this is the 1, this is a 0. So if this is rising edge is pushing, you are getting a 0. And if this is a falling edge, so this is, which means this is pulling, it's inverted, so this is pushing. And you are getting a 2 VDD over here. Okay, so the output of this inverter becomes 0 to 2 VDD. And if you look at the sizes of the transistors, and this one is 20 over 1 width to length, and this is 100 over 1, and this one is 100 femtofarads, and this is 1,000 femtofarads. The considerations for the design, the parameters designed for these devices. For this guy, it's only 20 versus 1, but this is 100 versus 1. The reason for that is because this point is driving another inverter as an output. Okay, so eventually this is the output. So it's driving the output. So we hope this is a bigger capacitor, have a stronger driving capacity. The same for this transistor. So I'm making this one wider. To drive the output. So this will be the important, some of the important points on the quiz on Monday next week. So first, the output over here is 0 to 2 VDD, right? And second, these two are larger and wider and larger to drive the output. And this one doesn't have to be big, doesn't have to be wide and big, because it's just driving the gate, okay, smaller. If this is M2, this is M1. It just need to turn it on. So not really running DC current. Remember, why do we prefer CMOS transistors over BJTs? The BJTs don't have a gate. It's base, collector, emitter. Right? So BJT transistor is a bit obsolete for integrated circuits. It's because it's directly connecting your terminal to the junctions. Eventually, it's running static currents through it. This is consuming a lot of power. However, for this one, it doesn't. It has a gate. There's no DC current. It's a dielectric material, right? Remember the cross-sectional view of it, right? So the gate consumes less power, right? So this one only needs to turn it on. It's not shorting to any of the drain and source in the P or N junctions. It's only shorted to the gate. So we don't need a big transistors or big capacitor to drive it. Just need to turn it on. All right. So we want to keep them smaller so we can have a smaller footprint of the entire circuit. And the third point over here is this guy, because the source of the PMOS can potentially go up to 2 VDD. That's a P plus. All the other PMOSes and wells are shorted to VDD. However, this guy can potentially go up to 2 VDD, so which is going to cause a pin junction, which is bad. So in that case, we want to connect the body of this PMOS to the source directly. So this PMOS has to be built in its own well, right? That's the third consideration for this circuit. And if we extend this circuit, given that this one is able to boost voltage from VDD to 2 VDD, so we can use this high voltage, relatively higher voltage, to drive to pass the entire VDD from the NMOS to the source terminal for the sample and hold circuit. So now let's draw that schematic over here. It's a gate, it's not a body connection, okay? It's a gate. Comes to this NMOS in the capacitor. Okay. This signal faces this phi naught, right? Right. So when this one is going up like a rising edge for this signal, if it's a rising edge, what's going to happen? These signal lines have the same phase. Okay, so this controls the gates of the inverters and NMOS, and this one controls the gate of the NMOS. Here, okay. If this is pushing, rising edge is pushing, you are getting a 2 VDD, right? So 2 VDD arrives here and arrives here. As 1 VDD, take a 2 VDD. What's happening? Remember, for the NMOS, if you have the gate voltage to be higher than VDD, you are able to pass the entire drain voltage to the source. You are not losing VTHN, okay? So this one becomes VDD. And because it's rising edge, so this is pulling as well. It's pulling to ground. This NMOS is pulling to ground. Whenever this voltage here is a rising edge, so this NMOS is pulling. And it's pushing, and you're getting 2 VD, which is perfect. This 2 VD is going to keep this NMOS wide open, so you have VDD available for this source, for this pin. So this is able to see this VDD and start pulling charges from the VDD. And also, because this is short of the ground, so you have the charges have a place to go. So whenever this is pulling, and this is wide open, and it's all on. So this channel is on. So this channel is on. So it's charging up the cap, and it's shorting this terminal to VDD to ground. So what's happening? It's like a waterfall, right? It's dumping charges from VDD to the cap. And eventually fill it up with a voltage across the two plates. And that voltage becomes what? Yes. Okay, now let's see this one. So the signal here is inverted compared to this signal. So whenever this is the rising edge, this one becomes the falling edge. So if this is the falling edge, PMOS is on. PMOS is on, right? Falling edge PMOS is on. You are getting a VDD. This point is being put up to VDD. So this is VDD. What else? You got a VDD, VDD. What's happening for the PMOS? On or off? This guy, on or off? Off. What about this one though? Rising edge, right? Same signal phase. Rising edge, this is on. This is on. And this is ground. So this is 0. Even though this is on, but this is 0, so 0 will arrive here, right? I'm missing one line here. You got a 0 here, 0 here, 0 here. They are all off. Okay? So what about the output? Which phase? Which phase? Hold. They are all off. So previously it samples and tracks and this getting charged up. And now at the rising edge of this signal, this one is going to hold that charge. You look at the simulation curve, it's holding that charge like a flat line. It's not changing. So it has nowhere to discharge. Okay, now let's look at this. When phi naught is the falling edge, what's going to happen? This is off. So you're not resetting your gate voltage. You're not resetting your gate voltage. I just want to remind you about this circuit. It's doing very similar thing because this one, you cannot just implement all the switches without any control. So that is why we are adding so many different things. Over here is the charge pump to boost the voltage. And these are all the switches that controls the sample and hold and track phases. Okay? And that's the model, and that's a real world circuit in your phone's camera everywhere. Okay, so whenever it's the falling edge, so falling edge, this one is doing what? Pulling. This is pulling, and this is pushing. Okay, this is pushing. Whenever this is pulling, you are getting what over here? It's gonna be VDD. Will be VDD. When it's pulling, okay, when it's pulling, there will be one VDD being passed through this NMOS and arrives as source. Okay, so you are getting one VDD over here. That's one VDD, one VDD, one VDD. Okay, that's one VDD. And because this is off, because the falling edge is off, so there's nothing going from ground to here. Okay, so this is not 0 anymore. However, for this one, this is falling edge, so this is rising edge. Since it's getting inverted, this is rising edge. So the rising edge is gonna turn on this NMOS. So basically, the signal here will be passed to this point. So you are getting S. If the signal here is S, okay, you are getting S. So here's S as well. Okay, and because this is on as well, right? Previously, I got a VDD stored over here. And because the signal is usually smaller than VDD, because you have some ADC, the maximum voltage is VDD, and you are not trying to, sample voltage at VDD plus 1 volt, right? So it's usually all the signals has to be within the range of the 0 to VDD. So the signal has to be smaller than VDD. So eventually, this PMOS is on, and this S is able to pass, because all these gates are on as well. Okay, these gates are on as well. So this signal, the signal voltage, is going to pass through this gate and being added to this VDD. So eventually, the voltage here remember from the last phase, this capacitor is storing a floating charge of VDD, and now you are adding this signal voltage, the little signal voltage to this VDD. So eventually this becomes like a pulling and pushing, right? So adding to this floating charge. So eventually this node over here becomes VDD plus S, because S is like a signal over here compared to ground, right? Similar to this one, is adding a V in to this VDD. It's adding a V into it when M4 is closed. It's the same thing. It's called a bootstrapped circuit. So VS is being added to this VDD, so this becomes VDD plus S. All right, and because this is on, this almost is on, so S arrives here, and also S is here, S is here, S is here, and the VSG of the PMOS becomes VDD plus S minus S, which is VDD. So there's no distortion for this PMOS. So the entire VDD plus S can pass through this PMOS and arrives here, right? So this point becomes VDD plus S, and this signal is being sent to the gate voltage of this NMOS. All right. So what's the voltage over here? S. What's the voltage here? VDD plus S. So what's the VGS of this NMOS? Yes. So we're keeping the voltage across S and G, or G and S, a constant. So we're forming a bootstrapped circuit for this NMOS, and also we are forming a bootstrapped VSG for this PMOS as well at the same time. So you can see this voltage at the floating charge, it was at VDD. However, when signal comes in, it's able to bump it to something larger than VDD. So there will be something different for this PMOS. And you guys let me know what you have to do. You don't need to do anything for the PMOSs in the inverter here and inverter here. Nothing has to be changed. They are in the same NWEL. So for this one, the body of this PMOS has to be changed. So the NWEL of this PMOS has to be separated from the NWEL of the other PMOSs. So which means you have to disconnect the NWEL of this PMOS from other PMOSs. So what can you do? What is the strategy for this? You see, these PMOSs, I don't even label anything, since by default, the NWEL of the PMOS of these PMOSs are shorted to VDD to avoid body effect, right? But for this one, it's different, because the source voltage, the source of the P plus of the PMOS is a P plus material, right? The P plus material. The P plus material has a larger voltage than the NWEL, which is shorted to VDD. It's forming a forward biasing PN junction. So you have to do this. You don't have other higher voltages. So the body of the PMOS, or the N plus, or the NWEL, has to be shorted to the source of the PMOS, because that's the highest voltage in the entire circuit. Okay, and it's constant. It's just, whenever this is getting higher, and your NWEL of the PMOS is getting higher at the same voltage, so the PN junction is never getting forward biased. So that is why whenever you are looking at the circuit schematic like this, there will be a PMOS having its own body connected to the source, which means this has to be placed in a separate NWEL because of that. But other ones, if they don't label it specifically, they are in the same NWEL. So that is why when we are looking at this very famous article published by another really successful electrical engineer, Dr. Gray in UC Berkeley. This is probably his postdoc. And this is the sample and hold circuit being used for billions of devices, probably perhaps in your smartphone's camera as well. And you can see in this schematic, you are looking at this schematic over here. None of the PMOSs are being labeled differently, except this one. So you can see this one's body is shorted to the source because it's being placed in its own well. Got it? Nope. So I need a quiz on it. Right. Yeah, so it's in one of the homework assignments, it's asking you guys to draw the cross-sectional view of the unwells. How do you place it in its own unwell, right? How do you separate it? It's asking you guys to draw the layout or the cross-sectional view. Any question on this? So the quiz today is really simple. It's from the lectures like a week ago regarding that a voltage doubler. Let's see if you guys can still remember what happened to that circuit.